So the speaker today does not need any introduction. It's Fernando. He's been with us already more than 3 and today is going to speak about discordant power of quantum evolution. That is a work that will be published just at the beginning of the year. Okay?
Hi everybody. I will do a long introduction so that you can understand, or at least understand where it's going with the details and so on. I'm going to use a measure of correlation, which is called the quantum discord, and doesn't have anything to do with entanglement, which is the usual one. And I will try to introduce where that comes from. And this comes from the measurement problem in quantum mechanics, and I will show you some examples. So the outline will be this measurement criterion for the classicality of correlations. So when the correlation between two objects are classical, purely, and then I will try to speak a bit of the 3 works that we have been doing on this subject. So to start with, the classical world can be summed up in this context in this way. Basically, the state of a system is given by a set of probabilities of having certain properties. So given probability to be in this state, or given probability of being somewhere else, and so on. We can know the state of the system by measuring it, and after the measurement, the system can be left unperturbed. A second look at the measurement result in the apparatus by another independent observer, for example, will yield the same probabilities and still leave the system unperturbed. We can all agree on the objective system, the state of the system. So in this sense, the classical objectivity is fulfilled with respect to a system and the apparatus which has measured it. So in this setup, we can say that these outcomes, so for example, measuring the position of something, if the outcome is this one, we can say that this collection of outcomes is classically correlated with those of the system.
This is a statistical description, this is a statistical mechanical description.
Yeah.
Usually in the classical system, what you have is the point makes space.
That,
you know everything. So this is just one point of view of looking at the system.
I agree.
Well, the other is a particular case, when the probabilities of delta functions.
Exactly. Yeah, it's more strict.
Yeah.
Why is this not quantum? Why you call this classical and not quantum?
Well, you will see, but I mean, and anything else which so this we all can agree after having a second look on the apparatus is not fulfilled in mathematics.
I think it's a matter of perspective. I don't know, you tell me, but I think that what you're saying is that classical is not something opposite to quantum, but it's a part of the quantum world. No, the presentation seems to be classical against quantum, and I have always thought that classical is the limit of the quantum.
In fact, the measure I will present is the one that tells you that when it's 0, this measure will tell you that the correlations have become purely classical. Yes, it's a reduction to a particular configuration. Do you want to understand it?
Now we understand. Quantum world is more complicated.
Okay, same thing in the quantum setting. Imagine that because of some miracle, your initial state is in a pure state, and the same thing for the apparatus, because this is the simplest case. And then, of course, in order to catch some information from the system and put it into the apparatus so that something is measured, they are made to interact. And the interaction can have, for example, this kind of form that this operator applies to the system, the other one applies to the apparatus. Now, if you expand in the eigenbasis of operator A, so in the system part, you can write it like this. So the psi 0 is CL-AL expanded, and because they are eigenstates of the operator A, you can already substitute in the evolution, you can substitute the eigenvalue, but the operator on B is still present there. So, and in fact, this is kind of like a conditional evolution depending on what eigenvalue has the other one, and it will evolve the apparatus depending on L. You can call this together, you can call it AL. So the apparatus correlates with the system in the basis of operator A. An example, simple example is a system that can be found in discrete positions. For example, with the eigenvalues XL of a coordinate, and you can put B equal to the momentum of the apparatus, and then what you will have is that you expand this eigenbasis, and this will be the evolution operator, which here I have represented an instantaneous interaction, which is just the displacement operator. So the apparatus, depending on the value, each value that has every eigenstate of the system, will feel a different displacement, proportional to XL. Okay? Now, if you trace out if you ignore the state of the system, the reduced state of the apparatus will be distinct. Okay. So, does this form already imply that we have measured the position of the system? Let's try to make a change of basis of the apparatus basis. So these AL, which are the displaced states of the apparatus, you just write them in another basis, which is orthogonal, and then you write the final state of system plus apparatus in terms of this new basis, and you can redefine this collection, so this superposition of the system state as another basis. So at the end you have also perfect correlation. So if I have M, so the M outcome in the apparatus, you could say that you have M outcome in the system. This is called the basis ambiguity problem, so which tells you that you are, until you do something else, you don't know exactly what you are measuring. So a measurement apparatus would be valid for any other basis, any other observable. Furthermore, if the state is entangled, and this kind of state is always entangled unless all of the F's are 0 except for 1, measuring the apparatus will perturb the system. So this argument of a second observer comes to the apparatus and measures the outcomes of the experiment and agrees with the first observer, this will not work. So the question is, what fixes the stable classical pointer basis, so the basis which defines the apparatus as a measuring object, in which anybody can check the properties of the system as many times as they like without perturbing the system? What we would be interested is to find a formalism, so a quantum formalism, which reproduces the classical situation. And at any point that we deviate from the classical situation, we will have a measure which will tell us how far away. So the resolution of this situation is, in terms of this pointer basis, one of them at least, is the fact that measurement apparatuses are huge, many body objects, and therefore they decohere fast, and fast is very fast. But this is orders of magnitude much faster than any population level changing or dissipation or humanization or whatever. The coherence is much faster. The coherence meaning losing the coherences between superpositions, basically. And in fact, we will see that the coherence in this is a kind of super selection, so dynamical one, on which kind of correlations are preserved after the coherence. So you have the system and the apparatus is so big that it decoheres very fast, and this decoherence will only allow some correlation between the system and apparatus to be preserved. And in fact, it is the interaction Hamiltonian between the apparatus and the environment which is dictating which kind of observables are allowed to keep correlations between what is measured and what measures. Basically, this can be expressed in a mathematical way, which is simply that if the Hamiltonian of this interaction commutes with the basis so any combination of the states of the basis, that is going to be the pointer one, then it will be preserved. So this basis is stable under the coherence, even if it will lose the coherences between different states in this basis, the basis will preserve the classical correlations with the system.
Sorry, I don't understand this formula because the left part of the commutator is a generic state of the apparatus, isn't it?
Yeah.
And
This means that, this commutation means, in general commutation means that the two operators inside it have the same eigenbasis. Okay. This ensures that no jump between the states in that basis are going to occur due to the evolution caused by this Hamiltonian.
but if instead of AL you put BL, the formula is still.
Yeah, the formula is still correct, and then it's BL, the basis which will be pointer basis.
I still don't understand.
No,
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 if it's
AI
here,
will
it's
satisfy this.
Yes.
Only a few bases AI will satisfy that they commute with the interaction Hamiltonian. That's the
Okay, I see that. Okay, the AL is no, I was wrong. A general superposition will be PLL prime, AL prime. This is a general operator. No, sorry, this is a particular form. It's a particular operator. It's not a general. It's not a general operator. Okay, I understand this.
This will be off diagonal term of the coherence,
general
and it will be destroyed in
This will not happen always. Only for some bases.
the diagonal, which is conserving the outcome correlation with the measurements and so on. So at the end, this suppression of superpositions and that this basis is conserved at the pointer basis will leave such a state. Here it's implicit that the environment cannot be traced because it's huge and you have no control over it. So this is the typical for all practical purposes statement. So the state at the end will be this one, meaning these are orthogonal states, the first thing, because otherwise this cannot be fulfilled. And this will, once the second observer, so first, second observer, whoever comes to the apparatus and checks these outcomes, they will know that if you have an outcome n, the state of the system will be this one. And this can be done as many times as you want without perturbing the system.
One question. Since what determines the basis of the observation is the interaction between the apparatus and the path, do you really need to have the apparatus to be a many-body object, big? Would be enough to have a smaller, not as small as the system, but with a strong interaction with the path so that it determines a basis which is well-defined for measurement? Would that be enough, or do you need also that the apparatus is very big and the coherence fast?
So one thing is the strength of the interaction, which will make the coherence faster, and another thing is the amount of degrees of freedom. And this is important, as you will see later in the example, we need to revisit the standard lag. This is important because the recurrence time, this is reversible evolution always. So, only if you not consider the path, then it will be reversible, but it's reversible. So at some point, everything will come back, you will have the ambiguity problem again. And because the apparatus and the paths are very big, this time will be huge.
But this basically means that the basis AL is infinitely dimensional almost if you assume a macroscopic TY.
Why not? In fact, if this is this position, it's already infinite dimensional, even if you have one degree of freedom.
Yeah.
So it's important that the path and the apparatus are big. Okay, an example. The reversible Stenger lag. Reversible, as you might know, the Stenger lag is based on a gradient of a magnetic field. You put in a neutral particle so that it has no charge, doesn't deflect because of being charged, but because it has a gradient, and if the particle has an intrinsic magnetic moment, or a spin, then it will go up if the projection is up, and it will go down if the projection is down. It will feel a force. This is a typical experiment where the wave function splits, and then you can see the two spots in the fluorescent screen. this is the reversible one in the sense that once the splitting has been done in the first magnet, there is another magnet which is deflecting the spin again back, and then once we are already here, the other magnet is in order that this goes back to the, otherwise it would go in a straight line. Okay? And we are going to consider that the initial state is a superposition of up and down, so that the wave function splits. And we are going to put a measuring apparatus which is going to be a two-level atom in the proximity of one of the branches, so that it will only interact with one of the possibilities. So the upper branch interacts with the atom and can be excited. So the atom is excited at the beginning, and they will prepare this superposition. So up times a combination of up and down, so excited, de-excited for the atom, the spatial wave function, or down with this thing excited and the other wave function. Depending on these things which depend on time, this is because the interaction is dependent on time, because it's lying near the atom, and when the interaction is finished, you will have accumulated a given phase. Let's say cosine of A, sine of A. Imagine you tune up the experiment so that these numbers here are pi halves. Okay? So that the cosine is removed and you only keep the sine. So the final state is this thing. It's a superposition between down excited and up de-excited. Okay? In this sense, this is what we were saying before, it's the apparatus is correlated. I mean, if you measure that the atom is excited, you know the spin is down, and vice versa. However, you can write this state in another basis, which is what we said before, which is the plus and y direction combination for the spin. And I mean, this is exactly the same. It's a combination of plus right minus left, defining like this. So this would be the eigenbasis for the sigma y operator, and this is the eigenbasis for the sigma x for the level population of the atom. So in these two expressions, you would have perfect correlation between outcomes of things which are completely different. I mean, here you would be measuring the z component of the initial state of the spin, and here you would be measuring the y component. So you have devised a standard lag in the z direction, which is measuring the y direction. So let us now add another atom, which is the environment. And you will see how this ambiguity is removed. For example, take this kind of Hamiltonian. This interaction is the identity for the spin, the system, sigma z for the apparatus, which is an atom, and then this one which can cause the transition from excited to de-excited of the environmental atom. Okay? This measurement, so this interaction is non-demolishing in the apparatus atom, because this, I mean, if the atom is purely excited or de-excited, this will only give a phase, and the evolution of the environmental atom will excite, de-excite, and so on, make transitions with different phases. You can see it in the evolution of the state. Evolution can be written like this: so up de-excited, some combination of the environmental atom excited, de-excited with given phases, and the opposite combination, so down excited with a different phase. Okay? If I choose the duration of this interaction to be such that A is pi4, you will have this thing. This, again, a perfect correlation between up, de-excited, something, down, excited, something else, which is the orthogonal. So this is a perfect correlation between outcomes. And now, if you try to put the same thing as before, seeing whether you can write it in another basis, you realize that you cannot. I mean, you cannot write it in a basis in which there is up, 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 or down, 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 or something like this.
Are you changing the branch head rotation, or what do you mean with the...
This is in order to not lose control because this is the environmental atom.
Okay, so basically to discriminate the two.
Yeah, this is,
Okay.
this is correct notation. Because
Not to get confused in the end.
instead of putting zeros and ones,
Yeah.
and this can be seen by projecting the state in the basis of the apparatus.
Mm.
So excited will give you something like this.
Yes.
So a perfect correlation between down excited and this other thing, which is the sigma y of the environment. And if you project to the de excited, you have up, de excited, and this other one. If you try to put the same in another basis, you are not able to write it like that. And in this sense, the environment is destroying the ambiguity. And furthermore, what is seen in this example is that the pointer basis is already determined, which is the one that lets you have the perfect correlation between outcomes of the system and the apparatus. This was made on purpose, of course, because this basis, which is the one that is selected by the environment to be the measuring basis, is the one that commutes with the Hamiltonian, because it's inside. Okay. A subtle point, of course, and this is where this revival time comes to, is that imagine that, because before in the simple case of only system apparatus, we chose a given name, and this, you can see that it's a fine tuning. So you let the upper branch of the spin interact for a given time, or you devise the experiment like this. But this environment atom, you have no control. So assuming that the interaction has been only for such a time that this is pi 4, this is unrealistic. In fact, if you put pi halves here, see what happens. Cosine disappears, this one disappears, and then you have that the environmental state is the same. So this will be a it will have this form. So the system apparatus will have a state, and the environmental atom will have a completely independent state, and therefore in this part you will have the same ambiguity as before. So you are going from no ambiguity, no ambiguity, ambiguity. And only when the environment is huge, you can say that this coherence time is higher than the age of the universe.
So,
I got through the question. Then the point, this example then is not, it has not the right properties of a true measurement, reversible measurement. So when you have only three, apparatus, system, and environment, each one with 1 degree of freedom, this is not enough. You say that you need the environment to be more than 1 degree.
It's never enough. Only that maybe you have to wait several times in the age of the universe to be back at the same point.
So the recipe to measure is to have some system, some measurement, and something else that will make the recurrence time larger than the measurement. This is the
relevant time for the system.
The recipe you cannot avoid it.
Exactly.
For practical purposes, it's all.
But still there is a difference, because it is clear that even if you cannot avoid these recurrences, if you consider different times, there is a given basis that will give you a result always. Sometimes you might have ambiguity, but at other times you don't have ambiguity. So that basis already is preferred, even if the system is not huge, to avoid these recurrences or whatever.
And this basis is the one that commutes.
Yeah. So that one is already set by the fact that you have just 2 atoms to be experimented.
Okay. Now, in general, what is the pointer basis of a given situation is not clear. You have to calculate it by hand always, or numerically, or whatever. But there are some examples which are known, which is, for example, the harmonic oscillator. Now, I will restrict only to harmonic oscillator being the apparatus and suffering decoherence into a heat bath. And there are basically three regimes, because there are three terms in the Hamiltonian. So it's if the Hamiltonian of the system is weak as compared to the interaction with the bath, the pointer states are known that will be the eigenstate of the interaction Hamiltonian. If it's the other way around, the pointer states are going to be the eigenstate of the system. This can be understood. And if they are comparable, you will have a compromise between the two. So for example, for typical spatially localized interaction, like for example an electric dipole interaction, so XX interaction, this would mean that for the first situation where the interaction dominates, the oscillator will tend to localize. Momentum diffuses and Schrodinger cuts disappear. In fact, you can calculate the master equation for the situation, and what you see is that apart from the unitary part of the evolution, the bath is introducing a very important term which grows with temperature, which destroys any superposition of contributions to the wave function of your density, which are in very far away places. So the farthest away, the more rapidly it will decohere. For example, a cat state, which is superposition of having a Gaussian wave packet here and the one here, will rapidly move to collapse into only one. You will have lost this superposition. In the second regime, dominating the Hamiltonian of the system, you will have something similar. So the decoherence is slower, and you will have something similar in Fock basis. So also something which is proportional to the distance in the eigenvalues of the Hamiltonian. In this case, the Fock basis. And in the third one, in which you have a compromise between the two, the coherent states will be the survivors of the coherence, and therefore the pointer states. And this is because the harmonic oscillator, you can imagine it as rotating in phase space, and even if the bath is trying to collapse to localize in position, this would translate into localization of some momentum and being a circle at the end. Okay, so summing up, this effective superselection due to the coherence of the apparatus leads to an unambiguous measurement basis, which is the pointer basis, which will leave you a state which is like this. And what I said, because this is stable against the coherence, second experimentalist can come and see the result of the measurement by checking the apparatus without changing the outcome correlation between the system and the apparatus, so that everybody can agree on the objective properties of the system. So the system has been measured to have property escape or this state, let's say, the probability pk. And whenever this it doesn't reach this structure, for example, by having this not being orthogonal, for example, which would mean that the coherence process has not been completely fulfilled, measurements will on the apparatus will perturb the system. And this is where the quantum discord will come. The quantum discord will be able to discriminate when this has happened or not, and how much you deviate from this situation. So quantum discord will be zero for this completely decoherent, classically correlated apparatus to the outcomes of the system. Okay, so at the end, this decoherent state, you can also write it in this way. The sum of projectors, so you can consider this as a projector until the state AK. It's the sum of the projector. If you do this operation, you can do it as many times as you want, and it will preserve this structure. And the failure to achieve this situation can be quantified by comparing two expressions which in classical physics are the same for the mutual information. One is this one, which is the Shannon entropy of one of the variables plus Shannon entropy of the other variable, ignoring so here ignoring the y, here ignoring the x, minus the total Shannon entropy. And the other definition, which is simply obtained by Bayes' rules, is the Shannon entropy of x minus the conditional entropy of x, so condition on the outcomes of y. And this is defined like this, and it's just the sum of all the possible outcomes in Y, multiplying the probability and the entropy of X, given that the particular outcome of Y has been this small y. So this is typical from Bayes rules. Because this, given that Y has been measured to have small y on the Y variable in quantum mechanics will perturb the system, these two expressions will not coincide, and will only coincide when you have this formal situation. And well, in quantum version is the same thing, but with the von Neumann entropy, and the conditional entropy is also defined in a very similar way. So probabilities of outcomes in the apparatus times the entropy of the reduced system give after the measurement with outcome I have been obtained. And this state after the measurement in quantum mechanics is just can be written something like this. If the measurement is orthogonal or projective, it's a projector and divided, normalized by the probability. Okay, so this is one way of justifying the quantum discourse. There have been some other ways, more quantum information oriented, or let's say more in the operational interpretational way. And this has to be compared with the separability paradigm. So entangled states are states which cannot be written like this. So a tensor product of one of the parties and the other party. And you will say, what is the difference between this and the other one? Well, these are orthogonal. Okay. In quantum mechanics, orthogonal means that something can be perfectly distinguished. And for entangled states, this is more relaxed. So they are not equivalent in general. Until some years ago, entanglement was supposed to be the key resource for quantum advantage in typical information tasks, like cloning, transporting, so many things, also in computation. But along the years, there have been lots of people developing some algorithms which have a quantum advantage, or quantum speed with respect to the classical counterparts, which are based on separable states. For example, there's an algorithm in which you have a collection of systems, which is in the completely random state, and you have another qubit, which is in an almost maximally random state. There's only a very tiny fraction, proportional to alpha, let's say alpha is epsilon, an infinitesimal, and with just a very tiny bit of coherence, of non-randomness, you put it into the system, make a Hadamard gate, do some unitary, and then at the end, by measuring here, you obtain the trace of this unitary, which is very hard classically. And this you have done with an infinite temperature state, and with something which is almost infinite temperature state. So quantumness. And there's evidence that in the whole protocol there is no entanglement at no point. In fact, there's some people who have given some evidences that quantum discourse could be the responsible for the speed up. And right now there are some reviews, there's a huge list of algorithms which give evidence that might be based on this measure. So some features of this quantity. As I said, it only vanishes for what in this context is called a classical state. A classical state is the one which has that form, or equivalently this other form in which this is a project. Okay, this is sometimes called also quantum classical because this can be whatever. If it's called classical, then it would have here another orthogonal project. Particular thing is that it's equal to entanglement for pure states. So anything which has been said in history about algorithms, computation, and so on with pure states is exactly the same for the image. The difference is with mixed states. Another fundamental thing is that this is asymmetric. Of course, because it comes from an asymmetric definition of everything. Also, nobody has succeeded in finding any explicit formula, so you have to rely still on minimization. Overall, Posimor, I forgot to tell this. but the definition is implied to be minimized on all the possible measurements that you can do on comparativity. So it involves a minimization, and therefore you have seen me many times in the cluster with 1,000 processes. It's because of this. Also, it has typically no sudden death, which is a characteristic of entanglement that after some time, when the coherence is present, entanglement will disappear forever. With this code, it doesn't happen because it's very hard to find a state which is purely classical. In fact, they have measures here. And something which I consider it's important, but nobody talks about much, is that the necessary and sufficient condition for master equations to be completely positive maps is that the system path state at the beginning has zero score. It was shown in some years ago.
What do you mean by master equations?
You got me there. Remember, Roberta? I mean,
Evolution of the
obviously,
reduced dynamics of the density of the system. You need always to derive the master equation, you always need to establish which is the initial condition between the system and the path. And normally you take factorized initial conditions, but you can of course establish a large array of initial conditions. And when you trace out to the effect of the environment, most of the time you do not have a positively preserving master equation. So when you try to establish which is the reduced dynamics, you need to do approximations to get a close form of the master equation. And the way to have it positive is that the initial condition or is factorized or it has zero score. That is, it increases the realm of the initial condition you can conceive.
okay, since I don't have much time, I will try to sum up.
Still have 30 minutes.
Okay, so basically we have done 3 works. One of them was establishing, we have seen that this code was the mutual information, so 2 different versions of the classical mutual information. One of them directly translates into the quantum one, and the other one we can call it J. And since the quantum mutual information is the total amount of correlations there can be between 2 systems, you can divide it between the discord, which you can call it quantum, and this other one which you can call it classical. So that when the discord is 0, these 2 coincide. And we were interested in checking what were the states that maximized the quantum correlation versus the classical correlation. So the ones that are extreme in this sense. And we found them. We found that they do not maximize entanglement, so the definition is inequivalent. And in fact, part of these extremal states are separable. In fact.
Which system is this? This is
2 qubits. Sorry. Yeah, everything I'm going to go is 2 qubits. Yeah, we'll. Yeah, in the definition of this code, as I told you in the conditional entropy, the conditional entropy is defined as the probability of having a given outcome of a measurement and the entropy of the resulting state. These measurements can be either orthogonal or general, which are called positive operator valued measurement, which is the most general thing you can have in quantum mechanics. And in fact, orthogonal measurements do not need to be the best in order to minimize the score. The score is defined as the minimum overall possible measurement. So you can take only orthogonal ones or more general ones. So for example, if you have a spin, an orthogonal measurement will be measuring in this direction or downwards. This would be orthogonal because this is the up and down state. They do not overlap. But you can also decide to measure, so up, down, and another one which is in another direction. It's redundant, or even that. it will be redundant, and each measurement will not give you maybe as much information as the others. But they are measurements that you have to consider them. And what we saw numerically and with some algebra too, that basically it doesn't add too much. So the conclusions of this work are that first, that extremal POVMs are rank 1, which is something which is hard to explain without time. And basically that the improvement that you do by considering more general measurements is typically of order 10 to the minus 6. And if it's higher, it's very improbable to find these kind of states. And the title of the talk is this thing, Discordant Power Quantum Evolution. We were interested in seeing which kind of quantum evolution, so unitaries, which are the ones which are able to produce from a system apparatus state which is purely classical the maximum amount of discord. So you put this system of apparatus, apply an evolution, and see which evolution is the one that gives you more discord. And we define it in this way. So the discording power of a given unitary is the maximum over all possible classical states of the discord once you have applied this evolution. This mu means that you are taking this at purity, at a given purity. Unitaries conserve purity. Purity is just the trace of raw square. So purity is 1 when the state is pure, can go to 1 over the dimension of the Hilbert space when it's completely mixed. And classical states have this form, so it's orthogonal here too. So this way, classical. And we have taken a symmetrized form for this discord. This problem can be approached through the Carpenter composition of a unitary of 2 qubits, which basically tells you that any unitary of 2 parties can be split up into something which is local rotations here, and a kernel which is non-local, so it applies to both parties. Since these local rotations do not change discord and can be absorbed in the definition of the basis, at the end what you have is that the discording power only depends on the non-local, so the 2-party effect. So all the gates with the same kernel will have the same discording power. And the important point here is you want to know for each purity how much discord you can produce from a 0 discord state. And there's a paper where they tell you that for each purity what is the state which has most discord. So you only need to find which evolution or which unitary goes from the classical state to these states which were found in this reference. And this we managed to do. And well, these are the states. I have time to explain. Basically, the most important thing that we saw is that there is a family of kernels of this form, and this means I didn't write it. Like the same thing in the Y, in the Z. You see this is the sigma x, so in party A, party B, same thing there. And with these numbers, this is the one that is that for all purities to reach the maximum.
So there was alpha x, alpha y, alpha z?
Yeah. And this is peculiar, first because you are able to find a unique family which is valid for all purities. And it's also funny that something which is typically considered to be a universal gate in the sense of quantum computation, which is the CNOT gate, which is this one, pi 4 and the rest 0. This one is not the best discorder for all purities. So it's one of the perfect discorders, so it's giving you the maximum for a given range of purities, but for a given range it isn't. Okay, so I conclude. Well, okay.
Sovietist tradition about first question. Students?
No longer. Cancel that. No longer.
No longer. Any question?
They are characterizing the most quantum operations on 2 qubits. Do you find any rule? For example, can you guess what will be the maximum entanglement between 1 gigabit computer? So, what is the rule to select? What is the operation between qubits that make the combination, the evolution, the most quantum? You have an intuitive rule?
No, nobody has. I mean, nobody knows what is the quantum advantage in that computation.
So maybe after looking at your solutions.
I mean, there are certain particular algorithms on which you have evidence that this quantity is the one giving you the advantage. There you can use this in order to fabricate these reserves. But it's very, very much debated what is the quantum advantage.
What is the rank? Rank 2, rank 1?
Yeah, rank 1 states are pure. So, I mean, you can always write down a state in the spectrum, in its own spectrum, so the spectral decomposition, and the projectors. So a pure state is one that you can write just as one of these. It's rank 1, if it has 2, it's 2, and so on.
Going back to the introductory part, you consider the apparatus being quantum, as different with the usual formulation of measurement process in quantum mechanics. But then, don't you have a second step, which is reading the apparatus? If the apparatus is quantum, then you do the measurement with this quantum second system, which sometimes remains in this peculiar state, but then you have an extra state, which is reading the apparatus. Are you introducing second?
I never claimed to have solved the measurement problem, which is this endless chain of what measures what, and then how do you know what has been measured, and then stopping in the brain or whatever. You don't solve that. The only thing that you solve with this setup is saying, okay, the apparatus will have an objective correlation which can be checked. If you can say the sentence, it can be checked, then it can be checked several times and it will not further exist.
But this is reading the apparatus, no?
Yeah, the sentence checking the apparatus, this is an unsolved problem.
This is at this step you will need some collapse or some this collapse postulate. So this is still a fundamental problem.
Yeah.
I have 2 questions. Well, the first question is related to this case that the C0 gate is not the maximum of this intertrapezoidal state. So is that state good for something beyond what the C0 gate can provide? I mean, can you do something with that state that has more discord in that case than the C0, the other state? Or you can do the same? Or?
There are things which you can do better with a state with discord and no entanglement than vice versa.
Yeah, but for example, in this case,
for example, the algorithm I told you, it works with no entanglement. The moment you have a bit of discord, it will work.
Yeah, but if you have more discord, it does not work better necessarily. I understand.
Yeah.
So the fact that you get an Earth state which has bigger discord than the C0 gate,
not so good.
Does not directly provide you a new sort of gate that has, I don't know, whatever additional property or.
In this protocol, so this tiny quantum part which you put in, the higher you have it, the less operations you have, the less times you have to do this.
So there is something.
But it's also not so simple to say the more discord, the better.
Depends on the task. It depends on the task.
Yeah.
Also, at the beginning you introduce everything from this perspective of the system and the measurement, to avoid this discord. But when you apply the discord to the C0 gate or whatever, to these two states, basically this is two states that they interact and you measure the discord, but it's not necessary to have a measurement to do that. No? I mean, it's just the two states itself. It is not that one state, it is not a big system and a small system. There is not a one measures the nodes. You just have two qubits to interact and do something. And there is no thermal bath, there is no measurement, there is nothing. So
this was the motivation of introduce this thing. Yeah. And then other people took this.
But then when me, at the beginning when you introduce, of course, this is asymmetric because there is one system and one big system, there's the measurement, which interact with the bath and so on. But when you apply to the two qubits interacting, then where is the symmetry, the asymmetry? The two systems are somehow the same. So it's just on the definition of the discord asymmetry, but it's not on the interaction itself. No?
Actually, there was the same year. There was also another author, the Draghelon, yes. That was introduced in the definition, it was not, I mean, I like more the context of system and apparatus because it clarifies the physical meaning. But you can give the definition of discord just telling, okay, two equivalent definition of the mutual information. Classically, they are equivalent. In the quantum framework, they are not equivalent. And they just take the difference. And you don't speak about system, apparatus, and whatever, but then you have a mathematical object and it's a bit obscure. The system apparatus interpretation of Zurich is more physical.
But in this case, two qubits going to interact in a single case, within two qubits, there is no system, there is no measurement, it's just two qubits at the beginning and two qubits at the end, and some protocol of interaction in the middle. And of course, depends on what you measure. What A affects B or B affects A is the two measurements somehow.
The two definitions of mutual information, you have called one of them classical, the other quantum, and you say that the difference is the discord. Why you call quantum to one of them and classical to other of them?
Why? Because one is always greater than the other. I mean, this one, which when translated instead of shaman to be like von Neumann, this directly translates, and it's always greater in value than the other one.
In the other one, there is the measurement playing a role.
Yeah.
I mean, in the other definition, you have the conditional entropy, then you need to have done a measurement of one of the two parts, and that is where the difference comes. Questions? Or